Okay, in this video, we're going to take another look at a function we've been working with in our homework assignments in finding the value of a function, say g, and using area to get that answer. So we're going to take a little deeper dive in looking at that kind of function. So what we've had before was say something like, let g of x be equal to the definite integral from 1 to x of f at t dt. And just simply put, we're given a graph of f, and it may look something like this. And this is where 1 is at. This is 2. And say that maybe this is 4. And if I wanted to find g at 1, I would replace x with 1. And we know that from 1 to 1, we have no area. So our answer would be 0. If we wanted to find g at 2, we would go from 1 to 2 of f at t dt, and we'll find this value of the definite integral by using area. And so I have a triangle. It'd be 1/2 times the base is obviously, no, we're starting at 1. So that's not 2. So from 1 to 2, the base would be 1. And let's throw this height up here at about 2. So then the area from 1 to 2 would be 1. So the value of g at 2 is 1. And we also consider things like g at 0 from 1 to 0 of f at t dt. If we're going to use area, which we are to get the value of this definite integral, it's best to reverse the bounds. So we integrate from low to high. And from 0 to 1, we can now proceed as normal, negating that value, though. So it'd be 1/2 times 1 times 2. And we look like we'd have an area or a value of -1. Okay. So now let's consider this, something a little more detailed. So suppose now I'm going to give you a function g, but the integrand for the function will not be a graph this time. So it won't be given a graph. So let's suppose we have g of x equals this definite integral starting at pi to x of cosine t dt. And to be quite simple about things so we understand, this maybe with some context, let's label this integrand function cosine of t velocity, okay? So if we were to evaluate this portion right here, that we know how to do, we'd rewrite it without the bounds and take its antiderivative, which is sine of t. We would then restore back our bounds in terms of x, not necessary to use a u substitution, obviously. And I'm going to evaluate my antiderivative, sine of t, at the upper bound minus the lower bound. So g of x, we now have an expression for g of x. G of x is equal to the sine of x minus the sine of pi. And we know by now that if this function is velocity, which I set up here, and the antiderivative of velocity is position, that this expression here would represent the change in position. But this time we have a formula for it. We have a function for it in terms of x. So if I wanted to know the position or the change in position, say from pi to 3 pi over 2, I wouldn't have to go back and redo things. I can just come down here and replace x with 3 pi over 2. And this answer, which this would be -1 minus 0, would be -1, would be my change in position, which would mean I ended up 1 unit to the left from where I started from. Doesn't tell me where I'm at, just talks about just tells me the change in position. And it would mean that I'm 1 unit to the left from where I started from at pi. Okay, so what we end up with here is a function g in terms of x representing the change in position. So we're going to take a deeper dive in trying to understand how this integral function, integral defined function behaves. So back in November, we talked about the behavior of a function, maybe such as velocity or acceleration. And when we examined how a function behaved, we talked about where a function was increasing, decreasing, a relative max, a relative min, an absolute max, an absolute min, where it was concave up, the graph, where the graph was concave down, and where we changed concavity, we had a point of inflection. So all of these words are associated with telling the story about how a function behaves. And I ask you now, what did we do? What was the very first step we did in trying to answer where functions increasing or decreasing, or where the function had a relative max or relative min? What was the very first step we did? What's that answer? We were given a function f, and I'd asked you, say, to make it simple, x squared plus 3x minus 1, where that function's increasing or decreasing, or possible extrema. What did we do? Well, I hope we would say that we took its derivative. We found the derivative, found the critical points, and did either a first derivative test or maybe a second derivative test looking for extrema. Well, now in taking a deep dive at these integral defined functions and understanding how they behave, we're going to take its derivative. So remember, I found an expression for g down here. I took the antiderivative, I evaluated it at the bounds, and I got this expression. So now g of x is equal to, we said, sine of x minus the sine of pi. And as we had just talked about, that in understanding how g behaves, I'm going to take its derivative. So g prime of x would be equal to the cosine of x, and this is just a constant. The derivative of that constant is 0. So my derivative is cosine of x. Let's do another one. Suppose g of x equals the definite integral from 1 to x of sine of t dt. Okay. So I'm going to rewrite this without the bounds. And the antiderivative sine is negative cosine. Bring back my bounds. Not necessary to do a u substitution. Put in the upper bound first. Minus cosine of x. Minus a negative becomes a positive. So here's my expression for g. What is its derivative? Well, g prime, the derivative of a c function's a negative answer, times a negative is a positive. This is just some constant that I can't do in my head without a calculator, so g prime is just sine. Is there a shortcut we could do? Is it always necessary that I have to take the antiderivative, evaluate it at the bounds, and then take its derivative? And trying to understand this is that the way we always check our answers to an antiderivative is by taking the derivative and see if it ends up with the function in the integrand. So if you look, I started with this, and I'm ending up with this. Before, I started with this, and I ended up with this. So the long story here, if I wipe out all of this right here, take all that out, get that out of the way, I could clearly see that this is what I started with, and this is what I ended up with my derivative. So if we see a shortcut here, that the derivative of an integral defined function where one bound is a constant, the lower bound is a constant, the upper bound is a variable, it's nothing more than the function in the integrand, which is sine, evaluated at the upper bound, which is x. So the long story short is now, if I'm going to find this, it's g prime of x would be equal to the function in the integrand, sine, evaluated at this upper bound x, times its derivative, which would be 1. Because we have to apply the chain rule, because if this upper bound was an x squared, that becomes an x squared, that becomes an x squared, and this becomes an x squared because out goes the t, in goes that. And this just still become positive cosine of 1. So then now what would my derivative look like? Well, the derivative of negative cosine is positive sine now of x squared times 2x. So now if this upper bound had an x squared and not just an x, its derivative again would be the function in the integrand, say it, the function in the integrand evaluated at the upper bound times the derivative of that, which is 2x. It's just not a 1 now. Okay, so that's what we have to tuck in there. So here we go. Suppose, for example, I have g of x equals the definite integral, say, from pi to root x, and it's going to say be, it doesn't really matter, the sine of t dt. So g prime of x is the function in the integrand evaluated at the upper bound, which has the variable, times the derivative of this, which is 1/2 x to the negative 1/2, or 1/2 root of x. We can't forget the chain rule. Okay, so that's the nice shortcut. I think intuitively it makes sense because you're taking the derivative of the antiderivative, which is spin you back to the integrand. Very, very important to understand that. But let's suppose now, where can I go here for a shortcut? Is if I come back here, kind of mutilated this problem here, from pi to x of cosine of t dt. And we know now by a shortcut that g prime is the function, the integrand, evaluated at the upper bound with that variable, times its derivative, which is just 1. But suppose these things were switched. The bounds were switched, that is. So suppose g of x equals the definite integral from x to pi now of cosine t dt. Okay, let's see what my answer would be. I'm going to take off the bounds, and I know that the antiderivative of cosine is sine. I'm going to evaluate it at my bounds, which would be from x to pi. And I'm going to now have the sine of pi minus the sine of x. Okay, so again, the lower bound is the variable, the upper bound is the constant. So then now g of x equals this expression. Well, the derivative of a constant is just 0. But the derivative of sine is cosine, and my answer is negative cosine of x now. So notice that as a shortcut, that if I just try to do the shortcut, g prime is not just equal to cosine now, but it's equal to negative cosine. So you could see that these signs are opposites because that shortcut works easily when the variable is the upper bound and the constant is the lower bound. Because when we put these in, the order has gotten switched from the original. So up here, the upper bound was the variable and the lower bound was the constant. So if we want to do that shortcut where it would match that, we have to switch the limits of integration. So we could see here that the difference in the answers is just off by a negative. And that's because the bounds were switched, where the lower bound is the variable and the upper bound is the constant. So let's, if we to be given something like this, suppose g of x equals the definite integral, say, from pi to x squared of secant t tangent t dt. And I want to find g prime of x. Okay, so if I'm going to find the derivative, let's make sure that I'm using this shortcut that we switch the bounds. Oh, I got them already in that order. So duh. So let's do it the other way. What I wanted to do was let's put the pi up here in the x squared, because that was ideal. So now let's again suppose that the lower bound is the variable and the upper bound is the constant. But I need it to be the constant to the variable. So I'm going to switch the bounds. And when I do that, we know that we put that negative in front to compensate for the changing in the order of the x's. So it's secant t times tangent t dt, but the negative gets put in front because I switched those bounds. Ooh, that's not g prime though. That's just g. G prime is now going to be the function in the integrand evaluated at the variable bound, which is x squared, times the derivative of this, which is 2x, but let's put that negative in front. And there's our derivative. Okay, so now let's do some examples. G of x equals the definite integral from 1 to t cubed. Let's make that x squared or x cubed times the sine of t times the cosine of t dt. You do not have to worry about taking the antiderivative. If we want to find the derivative, we know of a shortcut, which is called, by the way, the fundamental theorem of calculus part 1, which I'll note here at the end. It is nothing more than the function in the integrand evaluated at the variable bound, x cubed, times its derivative, which is 3x squared. That's it. Next one, suppose h of x equals the integral from, these can look really awkward, 2 to x squared plus 1 of, say, the tangent of t dt. Then h prime of x equals the function in the integrand evaluated at x squared plus 1 times its derivative of the inside, which is 2x. And one more, j of x equals, let's do here, x squared minus 2x to 3 of e to the t squared plus t power dt. This one you actually cannot take the antiderivative of. This is not of a closed form. We would not know of a function by what we know so far whose derivative would be that, e to the t squared plus t. We can't even do this one, but we don't need to worry about that in finding its derivative. So j prime of x, well, I've got the variable at the bottom, so let's rewrite that. Let's rewrite the bounds. And when we do that, we know we have to put a negative in front. So I had to do a rewrite, switching the bounds. So it's a constant to a variable. And I switched it and, of course, made it negative. Now I can do my shortcut where j prime of x is the function in the integrand. Out goes the t, but in goes the expression for x, which we do not need to simplify. times the derivative of that, which is 2x minus 2 in parentheses. Okay? So this we know as, finally, the fundamental theorem of calculus, part 1. And this is the derivative part. It says that if g of x equals the definite integral from from a to x of f at t dt, then g prime of x equals f of x. It's the function in the integrand evaluated at the variable bound, which is just x, times its derivative, which just should be in this case 1. And that is the fundamental theorem of calculus part 1. Part 2 was that if we're given the definite integral of a to b of f of x dx, and capital F is any antiderivative of lowercase f, then it's capital F at b minus capital F at a. So these are the two parts of your fundamental theorem of calculus. This is part 1, the derivative part, and this is part 2, which we've been working with, is the evaluation part. So I call this the evaluation part, where we take the antiderivative, call it capital F if you want, and we evaluate it at the bounds b and a and subtract them. This is the derivative portion. So now we're finally making a connection between the derivative and the function f. Okay. And again, they don't need to be of something we know how to take the antiderivative of. Like in this case, we can't do this. Not by a method we know of. So therefore, we don't need to worry about that. And finding its derivative, we don't need to worry about that. All we need to do is just recopy the function in the integrand, taking out that variable. Usually it's t, maybe. It may not be always t or something. And evaluating that function, the integrand, at the variable bound, and then timesing it by its derivative. But remember, for that shortcut to work, the lower bound has to be a constant, and the upper bound is the variable. If that order is not, if that's not the order, where the variable is the lower bound and the constant's the upper bound, then you have to switch the two and make it negative. Okay, so pause the video and check your understanding and see if you can do this problem. M of x equals this definite integral from the sine of x squared to a bound of pi of the natural log of 2t plus 1 dt. What would be m of x? So pause the video and see what you write down as your answer. Okay, so I'm going this time from a variable to a constant. So the first thing I need to do is switch the bounds, and I'll negate the integral value, being now negative. Now that I have it from a constant to a variable bound, its derivative, bring down the negative, is nothing more than the function, the integrand, evaluated at the variable bound, which is sine of x squared, times this derivative, which is cosine of x squared, times 2x. There you go. Okay, and I'm just trying to decide here about the calculator here. Take your calculators out, and I'll show you something here that we'll have to get used to using. Let me see if I can do a shared screen. Let me see if the app is open. It is. Okay. So anyway, let's go back to here and let's see graphically if some things make sense. So I'm going to go here to g of x, and I'm going to go math 9, and the lower bound is second pi. Oh boy. Delete cursor over that. Second pi. Wait, why is that happening? Should be just, believe I'm hitting pi. Yeah, there it is. Okay. And then this is going to be x. And this is going to be the cosine of x dx. So there's my integral. And I'm going to take its derivative. So it's going to be math 8 respect to x. Vars, y vars, function y1, or, second alpha trace. And then I'm going to take with respect to x. Okay. I'm going to turn off y1 by cursing over the equals and turning it off. So I'm going to take the derivative of my integral defined function. Pause the video and ask yourself, what should the graph be? All right, it should be the graph of cosine. So if I do, I'm going to do zoom trig and see how that works out. And there is my cosine curve right here, beginning right here. When x is 0, here's my one cycle of the cosine curve. Okay, and we'll talk more about that. All right, so that concludes this lesson, essentially on the fundamental theorem of calculus, part 1, the derivative part.